Hi, this is topic of assignment and it is a part of linear programming problem. And as you can see, this is question number 2, that is the second question of this type. And I have taken little advanced question where I would be able to cover the, all different things that you can find in a particular question. So this pretty much covers the entire chapter, this and the previous questions both put together. Anyway, so now let's just have a look at the question. Question is pretty straightforward and simple. Look, there are four executives. I am labeling them as E1, E2, E3, E4. And there are three territories, like T1, T2, T3. Okay? And this table over here is actually giving us the revenue potential of executive territory combination. Now, what it means is if executive 1 operates in territory 1, the revenue potential of this is 60. So for all such combinations, we have the entire data with us. Now, if you read the question, it says use Hungarian method and find optimum assignment. So now, first point to be noted is when I say optimum, I mean the best. So we want to find out best possible assignment of this executive to territories. Alright, so now let's get started solving these questions. Now, the first thing you should always do while you solve is write down comments. Now, the first comment that I'll write down is what is the question. The question is are we talking about revenue? Yes. So if it is revenue, we have to maximize it. The first point I'll mention that it is a revenue maximization problem. The point to be noted. Now, let's write down the second point that you clearly see there are 4 executives and 3 territories. And there is only going to be one executive in one territory, okay? And in that case, you can see that one of the executive has to be fired, right? Anyways, we'll see how that goes. Now check number of rows. Number of rows, there are 4 rows, E1, E2, E3, E4, and there are number of columns. The number of columns are only 3, and number of rows, number of columns are not equal. You say therefore it is unbalanced problem, and to balance it we add dummy territory. Okay, so what we typically do in assignment problem is whenever we are falling short of say one column over here, we simply add a dummy territory, and dummy is typically denoted by X. So I'm going to call my dummy territory as X, and I have to add a territory, so there's going to be one extra column here. So let me do that over here real quick. So I will have to attach a territory here. Okay, let's do some adjustments here and say that's a dummy territory. So dummy territory has to be X. And look, it is a territory that I'm assuming just so that I be able to solve the problem. So there is not going to be any revenue. So I hope you can guess that revenue of the dummy territory is 100%, it's going to be 0. So I'm adding a dummy territory with the revenue potential 0. Alright, so that's what we did. We added a dummy X here. Fair enough. Now, okay, let's go to the next one. Do you see that there is no restriction? Like, it is not mentioned that an executive cannot work in a particular territory. Nothing like that is mentioned. We have numbers for pretty much all combinations. So here it is unprohibited. That means there is absolutely no restriction like we had in question number 1. So that's good there. Alright, it is unprohibited, and now that we have added one column, we can also say the size of the table is 4 because there are 4 rows and 4 columns. Alright, so after having said all of that, now let's start solving this question. Now, how do we solve the question? First thing that I want to mention here, that in case of maximization, find regret table. Okay, so now understand this rule here. This whole method is built to minimize. So Hungarian method will by default minimize, of course, because we do row minima, column minima, it's all minimization. So this method by default is going to be minimization. So now when you want to do a maximize, like in our case right now it is revenue, and revenue has to be maximized, right? So in that case, what I will do is I'll have to find the regret table. So remember that in case of a maximization problem, always find a regret table. So let me quickly do the regret table. Let's find regret table here. It's like this. Okay, I'll also write down the procedure of how it is done. Okay, regret table is maximum value of table minus every value. So we'll take a maximum value of the table and subtract every value from that. So highest value of the table is 110. So you take that as a number and subtract everything from 110. Okay, always bigger number minus smaller, so it's always going to be positive. Let me quickly draw a regret table. So I get a regret table like this. This is 1, 2, 3 and 4. 1, 2, 3 and 4. Now let me do this calculation. The highest number is 110. Okay, you subtract 60 from that. That gives me 50. Then 110 minus 80. 30, right? So like that you subtract every number from 110 and write down what you get. So then, okay, so let me do that offline. Once you get the regret table, okay, now you can start solving using Hungarian method like how we always do. Okay, so the first step here is going to be row minima. So if I have to do row minima, it's the same procedure that take the smallest number of the row. The first row, the smallest number is 20 and subtract it from every value of the first row. Let's quickly draw that. 1, 2, 3 and 4. 2, 3 and 4. Now the smallest number is 20. 50 minus 20 gives me 30. 43 minus 20, that is 23. 20 minus 20 is 0. And 110 minus 20 is 90, right? Okay, so let's do that here as well. Okay, so smallest value of the next row is 15. Okay, so subtract 15 from 30. You get 15. Then 27 minus 15 is 12. 15 minus 15 is 0. And 110 minus 15. 110 minus 10 would be 195, right? Okay, so the smallest value of the next row, okay, the third row is 28 again. Now subtract 28 from every value. So you get 12, then 10, 0, and minus 30 would be 80. So it's 82, right? Okay, so it's 82. Alright, and the smallest number here is 0. So subtract 0 from all the numbers, it's going to be all same. So 25, 15, 0, and 110, all as it is. Alright, so we did the first step. Now let's go for the second step, and this is column minima. Now for column minima, it is exact same procedure as row minima. Now you just have to work vertical on the latest table. So always use your latest table that you have available. So you work on this and get this one. Okay, so well, 2, 3 and 4. Now smallest value here is 12. So subtract 12 from all these numbers here. This is 18, 3, 0 and 13, right? The smallest number here is 10. So you get 13, 2, 0 and 5. The smallest number is 0, so nothing changes, it's all same. And the next column has got smallest number as 82, right? Subtract 82. So 90 minus 82 is 8. 95 minus 82 is 13, right? And 0. And 110 minus 82 would be 28. Is that correct? Okay. So once you get the row and column minima done, now it's time to draw lines. So let's start drawing lines now one by one. Okay, so what is the rule of drawing lines? Let me write down the rule here. The rule says that cover maximum zeros with minimum lines. Now here I'm going to do that. I'm going to draw lines. Okay, line can be either vertical or horizontal, either or. And it has to cover maximum 0. So you can draw the first line over here, like this is the first line you will draw, and this line will cover 4 zeros. Okay, and then now just see there are only 3 zeros remaining. Okay, this one is covered already, so you have only 3 zeros. Just cover it like this, and that is your second line. The moment you draw a line, I hope you remember what is to be done next. Once you draw the two lines, you write down L. L is number of lines and there are two lines over here. Now once you see L as 2, N is the size of the table, which is clearly 4. It's a 4 by 4 table, so L and N is not equal. Since L and N is not equal, okay, you write down a statement. Never skip this statement. Always write it down that it is not optimum. Because for optimum, you want L and N to be equal, right? So it is not optimum, okay, and whenever it is not optimum, you need change. And the change is the smallest number of uncovered cells. So you have a lot of uncovered cells over here. So these cells are uncovered and these are uncovered. So out of all the uncovered cells where there is no line over them, like these are uncovered cells over here that I've highlighted, now you find out the smallest number of all of them. So the smallest number of all of them is 2, right? See? So now your change is 2. Now, since your answer is not optimum and what we want is optimum or the best, we have to change it. So now you have to modify this table and get a new table. And to modify, we have this factor, which we call it change. Okay, so the change is going to be of 2. Okay, with this change, you will subtract from uncovered cells and add at the intersection. I recommend you do it one by one. I'll show you how. Well, this is a new table here. But right now, do you see we have only 2 lines. So I believe it's going to be some lot of work. But anyways, let's solve this. Subtract 2. The change is 2, right? So subtract 2 from uncovered cells. From all these 4 cells, I'll subtract 2. I'll get 16, 11, 1 and 0. I'll subtract here, this is 6 and 11. I'll subtract here, this is 11 and 3. I subtract here, I get 26. Okay, so now the next rule says that add at the intersection. So you have to add here, so 0 plus 2 is 2. Okay, and remaining all the values, I'll just copy them as it is. So I'll copy everything else as it is, no change. Okay, so we have a new modified table now. Now always remember, refer to the latest table as I already said. So you will refer to this table now and work with this now. And work with this in a sense, basically draw lines to cover 0, cover maximum zeros. Let me do that here. Okay, so I can draw this line which will cover 3 zeros. And the next line I can draw is say this line which will again cover 3 zeros. And now there is only 1 0 remaining and you can cover this 0 the whichever way you want. You can draw it vertical or you can cover it horizontal. Let me cover it horizontal. So supposing if I cover horizontal, now always cover all possible zeros you have in a table. Now after you do that, count number of lines. So if you see here, there are only 3 lines. So you write down this whole thing that since L is equal to 3, which is not equal to N is equal to 4, N is the size of the table, L is number of lines. Therefore, it is not optimum. And not optimum is not a good thing because we want optimum, the best solution. Anyway, so we have to solve some more. And if you see, these are my uncovered cells over here. These are all uncovered cells. And it's the exact same procedure. So let me quickly solve this. And change that I have to find out from here, the uncovered cells is the smallest number, right? So let me write that down. Well, so change now is the smallest number of these uncovered cells. I see 3 is the smallest number here. Is that correct? Okay, so change is 3. Alright. And once you identify change, draw a new table or the modified table, which is 4, 3 and 4. Subtract change from uncovered, so change is 3. Subtract from here, that is 13 and 8. Okay. Subtract 3 from here, 6 minus 3 is 3. And this is subtract 3, 8, 0, and 26 minus 3 is 23. Alright, I did all of that. Now next what I will do is I'll add at the intersection. So add at the intersection is I'll add here and add here. So I already had 0. Now just pay attention to this. We already had the value 0, and when you add, you have to add change. Okay, the change is 3 itself right now. So when you do 0 plus 3, it's going to be 3. And 2 plus 3 is going to be 5, right? And just copy everything else as it is. So this is 0, 1, 0, everything else, whatever it is, as it is. Alright, 0, 0, and 0, and 0 over here. Alright. So we have modified. Now this has been modified like second time. First time we modified here, and then again we modified there. Okay, so the procedure is still same. So now you have to cover zeros over here. The rule is cover maximum zeros as always. So let's do that. First I have to make sure that I cover maximum zeros while I draw the line. So I have to be a little careful while you do that. I can draw either this vertical line here, or I can draw this line that will cover 3 zeros. I can just do either of the two. Alright, so okay. So let me do this line which covers 3 zeros. Now the remaining zeros I can cover either these two, or oh my god, I just have to solve one more time. Okay, I covered these two now, and I cover these two. I still have 3 lines. It is really going to taste my patience right now. Since L is equal to 3, that is not is equal to N is equal to 4, you say therefore it is not optimum, and we have to solve some more. Can't help it. So now we have uncovered cells. Uncovered cells are, these are the uncovered cells, and we have to identify change. Change is the smallest number of the uncovered cells, which is 1. Okay, so now we will have to again modify the whole table. Let me do that. Okay, don't lose patience yet. Alright, so 4, 3 and 4. Now subtract change from uncovered cells. So you get 12, 0, 2, 10, 8 minus 1, 7, 23 minus 1, 22. Okay, now add at the intersection next. So you have to add here and here. So we get 0 plus 1 is 1. So whatever is the existing number, you will add change to that. So you get 5 plus 1, which is 6. And now just copy the remaining numbers as it is. So it is 8, 0, 0, 3, 0, 0, 0, 0. Now here I strongly recommend that you do it step by step. First subtract from uncovered cells, then add at the intersection, and then copy down everything else as it is. Well, we got a new table again, and now once we get the new table, we again have to draw zeros, draw lines to cover maximum zeros. Let's do that for effort. Now these two, I have only maximum 2 zeros over here, 2 zeros over here, and 1 0 over here. I see it is over now. Any whichever ways, like supposing if I draw like this, I covered these two, that's maximum I can cover. I can cover these 2 zeros like this, say vertical. I can draw whichever way I want. Just have to make sure that cover maximum zeros with the minimum lines, and then there is 1 0, I can do it horizontal. And finally, yes, right, so this is number of lines 4, and that is exactly is equal to n. So L and N is equal. Since L and N is equal, therefore it is optimum. And of course, once we get optimum, okay, reason to smile, because we don't have to solve anymore, because we got what we wanted. We wanted optimum, and we got optimum. All right, so this is pretty much what the solution is. Now all we have to do is we have to write down the final solution, and to write down the final solution, I am really running out of space, but let me draw a 0 table here. Okay, so maybe I'll just skip drawing 0 table. I really don't have, I have to finish this problem over here. So now I just skip drawing 0 table. Instead, let's just write down the answer straight from here. Okay, so you have E1, E2, E3, E4, T1, T2, T3, T4, not T4, that's X, right? Just avoid this, I mean draw 0 table like how we did for the previous problem, but let me quickly wind this up now. Do you see this is a lonely 0? It's a 0 alone in the row, so I have to do this allocation here. So I'll do allocation E1 works for T3, and once you do that, you cannot allocate here. So, well, find out next 0 that is lonely. Okay, this 0 is lonely. It is alone in this column. So you can select this 0. Well, then you can cancel out this. So now you have 1, 2 and 3. So this 0 is lonely because it is alone in the row. Okay, so I can select this 0, I can cancel this out, and then the last 0 remains is here. So now these are my allocation. You can clearly see E1 should be working in territory T3. So now the last is, I'll write down the final assignment. Don't skip 0 table. That's much better. And anyway, so final assignment is going to be that E1, the executive 1, should be working in T3. Okay, and executive 2, E2, should be working in T1, and E3 should work at X. I hope you see E3 is working in dummy territory. So it basically means that E3 is the one who's going to get fired. Anyways, E4, executive 4 is going to work in T2, territory 2. Now, once we find out the final assignment, we should again go back to our original table, the revenue potential that we have for each combination. And let me write down the revenues here. So revenue for each combination, E1 T3. So E1 T3 is 90. Let me quickly write that down. E1 T3 is 90. E2 T1 brings in 80 as the revenue. E3X, of course, it's a dummy, so no revenue, it's 0. And E4 T2 is going to be 95. So that's the total revenue here. So this is just add them all. So 180, 200, 260, 265. Is that correct? 265? I think so. So this is the total maximum revenue of the assignment that we figured out after solving this question. So that's how it is done. All right. The only difference of this question is now since it is revenue maximization, the method will work, but we have to just find out a regret table before we go on solving with the Hungarian method. That's the point to be noted. Okay, this is actually the simplest part of LPP. Okay, assignment is the easiest of all, but I hope you followed this whole procedure very well. Okay, and if you have any queries, if you have any doubts, you can always feel free to reach me. All right, so all the best.